So today, let's really quickly review what we talked about last time. First things first, we talked about the difference between a deactivator versus an activator. So an activator just makes the benzene ring more nucleophilic, whereas the deactivator makes the benzene ring less nucleophilic. And we talked about how activators are electron donating groups and deactivators are electron withdrawing groups. And then the kind of more complicated thing that we talked about was directing effects. So we talked about the differences between ortho-para directors versus meta directors. And we put all of our substituents into categories. So we have our ortho-para donating groups, which give a negative charge to the negative position, to the ortho-para positions, and that's why they direct ortho-para. And then we have our halogens, which are actually electron withdrawing groups. However, they still do resonance and form negative charges on the ortho-para positions, so they are still ortho-para directors. And then the meta directors are going to be all of the electron withdrawing groups besides halogens. And the reason they direct meta is because when they do resonance, they form a positive charge on the ortho and para positions, which make them super electrophilic. And that by default makes the meta positions more nucleophilic. And then we basically put those terms together, and I didn't write it down. I guess I'll just do it verbally again. So actually, I lied. I did write it down. So then we put those things together and we said we have our, sorry about that. I can't get it to stay on the screen. Okay. We have our ortho-para activators, and those are all the donating groups. They make benzene more reactive. They direct ortho-para. Then we have our ortho-para deactivators, which we also call our weak deactivators. These are only the halogens. They direct ortho-para, and they still make benzene less reactive. And then we have the meta deactivators, which are going to include all of our withdrawing groups besides halogens. They direct meta, and they make benzene less reactive. And we're going to call these guys our strong deactivators, and we're going to call these our weak deactivators. So it is important that you have that distinction noted. And then we did an example here so you guys could see what exactly I mean by directing groups and whatnot. So if we have a benzene ring with an OH on it, we talked about how that's a donating group. So that's going to direct ortho and para, and it's lagging just a tad, but it should be okay. And if we were to do a bromination reaction, we could either add the bromine to the ortho position or to the para position. So any questions about that? That's just kind of recapping what we did last time. Yes. So I like to put it like this, but I have two different tables because people see it differently. So in my head, this is the one that makes the most sense because I like putting things into boxes. So these guys are in the ortho-para activator box because they all have lone pairs. So that donates via resonance. And then I know that our groups do not have a lone pair. They actually donate via induction. And then the ortho-para deactivators, those are just halogens. So I memorize that those are halogens. And then for the meta deactivators, how I kind of look at it is these are all the carbonyls, right? So they are going to steal electrons. And then these guys just have a bunch of garbage going on. And so they're big, bulky, electronegative. So I know those are going to steal the electrons for themselves. And the bigger and bulkier and more disgusting they are, the more deactivating they are. So this is how I like to think about it. But I know that some students prefer to think about it in this kind of linear fashion. So here we have the most reactive group, the strongest activator. And then as you go to the right side, you have the strongest deactivator. So this is essentially the best benzene ring. This is essentially the worst benzene ring. And regular old benzene would be right here. So whichever one works for you. Did I answer your question? Okay. Coolio. Any more questions before we move on to today's stuff? Cool. All right, so we did this page. I just did it like on a different page. We also did these resonance structures. This one, we actually didn't do the nitro group. We did a carbonyl, but it's the same exact resonance structures. If you want me to go over it, we can, but I think for the sake of time, it's not super important. And then here, I just gave you a more clean drawing of the same thing I had on the other page, and there's nothing really to fill in. It's already in order for you. And then this is supposed to be the instructions for the next page. So for the next page, all we're doing is drawing the final product for the given reaction mechanism. So we're essentially just going to go through now and do a bunch of practice. So the way I do each one of these questions is pretty much the same. So first things first, what group is this? It's a methyl group, cool. So is it orthopara or is it meta-directing? Orthopara and, oopsie. Is it an activator or a deactivator? Yes. So it is a weak activator, but for the purposes of like keeping everything kind of more concise, all activators are considered the same. Strong and weak deactivators are the ones you really have to note. But it's good that you know that methyls and stuff are pretty weak. All right, so once we have ortho-para activators, I then go in and draw an arrow on the ortho positions and on the para position, because those are the possible places we can substitute. Next thing I do is, what kind of reaction is this? Bromination. So what do I add to the ring? Just a Br, cool. So we could have two possible answers, and they are the ortho and the para product. And technically you could have two ortho products, but they are going to be exactly the same molecule. So I'm just going to draw one of them for you. Br. Br. And I will write underneath, just for the first couple, this is the ortho product and this is the para product. I did do it a little bit fast, but is there any question about how I did this? Yes. Wonderful question, and no, it does not, because there's only one substituent. So both of these would be symmetrical. And same exact thing goes for meta. So if this was to replace the meta position, it would be symmetrical on both sides. And something I briefly mentioned last time is Dr. West considers this to be a 50-50 split between the products. And very briefly, just to recap what he says, there's technically two ortho positions, right? So statistically speaking, there's double the chance that it'll land on an ortho position because there's two of them compared to one para. However, if we talk about sterics, the para position is favorable because it's further away from this. So if you put those two things together, we can say approximately this is a 50-50 split. Does that explanation kind of sort of make sense? I'm getting a couple nods, so that's good. All right, cool. Yes. No, so the only time you really need to distinguish like where the lines in the benzene are is if he specifically asks you a question about the different hybrid structures of the different resonance structures of benzene. So in these kind of answers, you can draw them wherever, as long as you have three. Okay, so NO2, what kind of group is NO2? Oh, that's what I meant to do. Is it a activator or a deactivator? Strong or weak? Yes, so it's a strong deactivator, which means it directs where? Meta, cool. All right, so meta compared to that position will be here and here. and SO3. What kind of reaction is this? Sulfonation. I'm glad Kareem's not here to check my spelling. I'm 100% sure that's wrong, but I do not care. So we're going to have one answer only because, like we said, the two meta positions are exactly the same. So I'm going to go ahead and draw NO2. And on one of the meta positions, I'm going to put what? What do I add onto the ring? Say it louder. Okay, I heard you, so I'll give it to you. SO3H. So it's very important to remember that you do add that hydrogen at the end. So let me zoom out just a tad so you can see both of those together, and I'll give you a minute to do that. Any questions whatsoever? There's no such thing as a dumb question. If you're at all confused about anything, I want you to tell me now. Yes. The H, yeah. That's a really good question. Okay, cool. So the next one we're going to do, and if you need me to scroll back at any point, please feel free to let me know. So right here, we have chlorine. Is that an activator, strong deactivator, or weak deactivator? It is a deactivator, but it's weak because it's a what? Halogen. Cool. Okay, so where does it direct? Orthopara. Cool. So it's an orthopara weak deactivator. And this reaction, what kind of reaction is it? Yes, so every time, sorry, I don't know why it's being so annoying today. So every time I see something like this, first thing I want to do is write Friedel-Crafts, and we'll say alkylation. Alrighty, so the big thing with Friedel-Crafts, when can it not occur? NO2. Okay, so yes, any strong deactivator and NH2. Yes, that's a weird one because that is an activator, but doesn't count for Friedel-Crafts. So is this okay to react? Yes. So we can react and we can attack this position, or this one. So we can have two products. And for Friedel-Crafts, I'm actually also going to draw out the electrophile because, as we know, it's going to be a carbocation, and we want to make sure we don't get tripped up by any rearrangements. So in this case, we have 1, 2 carbons. We get rid of the chlorine and we add a plus charge. Is there any sort of rearrangement we could do? No. So all we're going to do is add 1, 2 carbons, 1, 2 carbons. And this is the ortho product and the para product. Yes. Great question. So NH2 is actually going to be too strong of a base to react with this. So instead of doing this kind of electrophilic aromatic substitution, it'll just react with a carbocation and do an acid-base reaction. The answer would just be no reaction. Because the thing with these kind of questions is he's not asking, is there going to be any reaction at all? He's asking, is there going to be this kind of reaction? So that's why you would say no. And then I saw another hand. Yes. NH2 and any strong deactivator, it will not occur. Correct. Okay. So the next one, what kind of group is this on the benzene ring? Activator, strong deactivator, weak deactivator. It's a deactivator. Cool. Strong or weak? Strong, because it's not a halogen. Cool. So strong deactivators are always going to direct where? Yes, but that wasn't the question yet. You're jumping ahead of me. So this would be a meta director. And this is actually going to be no reaction because what kind of reaction are we trying to do? Not alkylation, the other Friedel-Crafts one. Acylation, cool. Because remember, alkylation is just a carbon chain. Acylation is going to be a carbonyl. And why can't it happen, Anthony? Okay, you do know, you totally do. Okay, fine. So yes, as the book says, Friedel-Crafts reactions cannot happen with any strong deactivators. So this would be no reaction. Okay, I tease, but is there any questions about this? Yes, Dustin, what's up? Yes, so Friedel-Crafts acylation cannot happen in this case because we have this carbonyl on the benzene ring, and since it's a strong deactivator, this reaction cannot proceed, so we get no reaction. And then I can zoom out just in case anyone missed any of these. Okay, I guess I'll zoom out more. There we go. Okay, so while you guys are finishing writing or thinking of questions, I like to organize chapter 15 in like 3 tiers, right? So the first one, the base level, is just simple single substitution reaction. So just knowing the 5 different mechanisms or the 5 different reagents and the reaction mechanism. The second tier is doing a second substitution. So knowing what the directing effects are and knowing activators and deactivators. So this is tier number 2. So before we move on to number 3, which is like the hardest stuff, does anyone have any questions whatsoever? Okay, if not, the third thing we're going to do is we're going to do a third substitution, and we're going to do retrosynthesis, which sounds terrible, but it's not that bad. There's just one big concept that students tend to like get a little bit confused, so I want to talk about it right quick. So I'm going to jump back into this for a second. And here I have it in order of most to least reactive, right? So first of all, I want to get some terms straight. When I say that this is the most reactive, I'm talking about that benzene ring with that substituent is more reactive than any of these other substituents, right? And when I say this is least reactive, I'm saying that that benzene ring itself is the least reactive benzene ring of all the ones here. When I say this is the strongest activator, I'm talking only about the substituent. So this substituent is more activating than all the rest of these. And when I say this is the strongest deactivator, I'm saying that this group deactivates the ring more than all the other groups. Is that okay so far? All right. So when we're doing a third substitution, we're going to actually have to look at the 2 groups we already have on the benzene ring, and we're going to have to decide which one is more or less activating. So either take a picture of this or write it down. I will keep referencing this, but I want you guys to have it to look at on the side as well. It's also in the handout, but I think this one has a couple more molecules in it. So I'll give you a sec. That is so uncomfortably loud. Okay. So, okay. For example, this first one, right? We're going to approach it in almost the same exact way. So this guy is a what kind of group? Activator, weak deactivator, strong deactivator? It is a strong deactivator. Cool. So where does it substitute? Meta. Cool. Now I'm going to do this guy in a different color. Activator, strong deactivator, weak deactivator. What do we think? Strong deactivator. Cool. So if you didn't know that this was on the strong deactivator list, what would have given it away? Positive charge. Cool. Positive charges are always deactivators. Cool, cool, cool. So like I said, when we're doing a third substitution, and just in case anyone didn't see, for all the reactions we're about to do, we're doing a halogenation. So I'm going to do a bromination for each one. Yes. Yeah. So it's actually going to do both. Nitrogen it's so electronegative and it has that plus charge and it really doesn't want to. So it's stealing all the electrons it can. What you have to remember is that this ring will donate through resonance, whereas these guys donate through induction. So like we were talking about strength of withdrawing or donating groups, these are not going to donate as well as the benzene ring can. So it's going to steal all those electrons. You're welcome. All right. I don't remember what I said and what I didn't say, but all these reactions that we're going to do a bromination. That's why it's not written for every single one. All right, cool. So if you will look back at the list I gave you, which one of these groups, actually we'll do this first one together. Remember CN and N+. Let's go back to the list. And my question, it's not on this list. Darn me. It is, yeah, I'm just opening it up. Okay, so which one is going to be, thank you, what would I do without you guys? Okay, cool. So now for real, which one of these is more activating? And I'm zooming out just a tad. Ooh, okay, so some people said it, but I hear a little bit of like, ooh, okay. So when we're reading this list, I'm gonna highlight it in purple. We're gonna follow this line. So the most activating group, the strongest activator is up here. And then we're decreasing, and then decreasing. So this is the strongest deactivator. So whenever I ask a question, like I give you two groups and I say which one is a better activator, even if they're both strong deactivators, the answer I want you to pick is the one higher up on this list. And so as a couple people said, between CN and N+, CN is higher on the list. So that's going to be the strongest activator in that case. And also, if you guys want to take a picture of this one, that was my bad that I didn't show it to you. Okay, I got nervous. I thought I wasn't recording for a second. So back here, what I'm going to do to denote which one is the most reactive, I'm going to put like a little star by it. So what this means is that that group is the director. So in relation to that group, we're going to add the next substituent, meta. So right here. Or this is the other meta position and it's already taken, so we have only one possible spot to substitute. Are we cool? Do I need to repeat that? Okay, so since this guy is the more activating one, that one is going to be the director, which means that the next group will add meta in relation to this group. So this is the meta position and this is the meta position. This one's already taken, so we have to substitute here. And just as a reminder, we're adding a BR. So I'm going to go ahead and draw the ugliest benzene ring ever. And then I'm going to add my substituents. And I will add bromine right here. Yes. So if he were to give you one like that, it would, okay, so I'm going to answer your question while like using this as an example. So in this case, either one, whichever one you picked, this is the meta position for that one, right? So it's kind of like double meta. So if he gave you something that was the same groups or equal strength, they would be pointing to the same spot. So you can rank activators, but let's say you had two OHs, right? They're exactly the same. So they would have like, they would be pointing to the same spot. And we'll see a couple examples like that in a little bit, but if I don't answer your question by the end of it, let me know. Okay, cool. Any other questions? All right, let's do another example. So we have this guy. Is it an activator, deactivator, strong, weak? Yes, it's a strong deactivator, so it's a meta director. And what about this one? First of all, what functional group is this? An amide, cool. So amides can actually be donating or withdrawing groups. How do we tell the difference? Yes, depending on where it's attached to the benzene ring. Cool. So in this example, it is attached at the carbonyl carbon, which means it's what? Deactivating. Cool. If it was attached to this side, then it would be activating. If you have any questions about that, let me know. So this is also a strong deactivator. It's also meta directing. Which one of these guys is a weaker deactivator? And we can go back and look at the table together. So between these two, we're looking at this versus, I believe it was this. So which one is a weaker deactivator? Yes, the amide, because that one is on top. So when I say the stronger activator and weaker deactivator, those are synonymous. He uses both of those terms and they are interchangeable. So strongest activator and weakest deactivator. Those mean the same thing. So yes, okay, so we're looking for the strongest deactivator or the weakest deactivator, which would be this one, because it's higher up than this one. I just want to make sure you guys are good with like the terminology. It's the weakest deactivator. Yes. I know the word, like the verbiage of it can be super confusing, and that's what students tend to get confused on. So yes, between these two, this one was the strongest deactivator, and this one was the strongest activator. So this one is the director, and it's directing meta. So meta in relation to this spot is here and here. And it could theoretically do either of those spots. So we're going to have two products. And while I'm drawing that, I heard a couple of people being like, what? So questions, clarifications, anything? Yes. Give me 1 second to finish writing, and then I will, like, from the top, just say it one more time. It just occurred to me that I could have absolutely just copied and pasted this, but I didn't think of it. It'd be like that, I guess. Okay, so we could have the bromine on this spot, or we could have it on this spot. And well, actually, I'll give you a second, then I'll say it. No, I didn't want that. Yes. So for the ortho-para stuff, we did talk about it, and it was 50-50. For these ones, it is a little bit different because, one, they're both meta, and there is a huge like sterics problem. I don't think he's going to ask you which one is like more favorable, but you should know that this one has less steric hindrance, so that one would be better. But it's not like he'll give you both of these answers and say, like, only pick one of them, you know? All right, so one more time from the top. When we are looking for the director is, you know what? I'm going to write that down because I don't know why I haven't been. So the director is going to be the strongest activator, aka the weakest deactivator that's present on the ring. So when you're looking at that table, whichever one is like higher up on the table, that's going to be less deactivating. Therefore, it's by default the strongest activator. Yes. Deactivator. AKA. You know what, guys? I have that doctor's handwriting, okay? Kidding, yes. Okay, sorry, I didn't see your hand. No, so for these guys, we're specifically deactivator and activator are talking about the substituent. And we're talking about whatever two substituents are present. Yes. I don't know why I started out with only deactivators. I put these in a really weird order, but there's a couple different combinations. Let me just, yeah, there's like 2 pages of stuff, so we'll do some fun ones. Yeah, so if you want to think of it like in like the actual chemistry kind of way, what you should think about is for orthopara director, let me pull this up while I talk about it, just so you guys have something to look at. So for the orthopara activators, the higher it is on this list, the more donating it is, right? The more donating it is, the more nucleophilic those ortho and para positions are. For the meta deactivators, the lower it is on this list, the more electrons it's taking away from the ring. So the meta position compared to this one is really, really unreactive. Compared to this one, it's kind of unreactive, but it'll still happen. So if we were comparing this one and this one is going to be the director because the meta position compared to this one is more reactive than compared to this one because there's more electron density. Is that a little bit more helpful? Okay, cool. Any other questions? They've all been super great questions. So, cool. All right, let's do a couple more examples. I am going to skip a couple, but don't worry. We're going to do all the important ones. So this one right here, let's start with this guy. So this is an ester, and esters work just like amides. So this time, instead of being connected to the carbonyl, it's connected to the oxygen. So is it a donating or withdrawing group? Donating, awesome. And we know it's a donating group because it has these lone pairs. So since it's a donating group, is it an activator or a deactivator? Activator, which means it directs where? Orthopara, awesome. So activators are always going to be orthopara. Yes. Okay, so lone pairs are like the biggest giveaway that it's a donating group because those lone pairs are going to resonance into the ring. So bam, bam. Makes kind of sense? Okay. Okay, okay. I completely forgot what planet I'm on. Yes, okay, so the lone pairs donate into the ring. They're donating groups. That's why they're activators. We can keep talking about it if anyone wants to, or you can just email me. I promise I'll start reading my email. But moving on, this one is a methyl. So is that an activator, deactivator, activator? Cool. So it donates, it directs where? Orthopara, cool. So without even looking at the table, which one of these is going to be the strongest activator? The yellow one. Cool. Some people said the methyl, and that's okay, but what I want you to think is we have an R group versus a lone pair. Lone pairs are always going to be more activating than this guy, because this donates through resonance. This donates through induction. And I can write that down right quick. Donates via induction, whereas a lone pair donates via resonance. So since the ester is the stronger donating group, or excuse me, the strongest activator, life is so hard. Okay. It is also the director. So we're going to direct our group ortho and para compared to the ester. And I'm going to erase, oh my gosh. If it moves one more time, I'm going to start crying. I spoke too soon. Okay. So yes, we're doing ortho and para compared to that guy. So this is the ortho position, this is the ortho position, and this is the para position. So we can have how many products? Aha! So the people who said 3, it's a trick question. Why is it only 2? It's not symmetrical. There's another reason. Yes. Okay, cool. So please listen. So theoretically, there's 3 spots, right, that we're pointing to. But in reality, you are never going to substitute between 2 pre-existing groups. So if you have 2 groups with 1 carbon in the middle, you're not going to direct here. So I'm going to go ahead and give it a big X. So again, just to repeat that, theoretically, we have 3 spots that we could substitute. However, there is too much steric hindrance between these 2 groups. So you are not going to substitute in the middle of 2 pre-existing groups. And so I'm going to start drawing the products, and if anyone needs me to restate that, I definitely can. If you have a hand up, I cannot see you. So yes, but whatever you're adding, it's going to be exactly the same thing. So the reason we're doing the same reaction is just for like consistency. But if it was a sulfonation, you'd just add SO3H. If it was nitration, you just add NO2, etc. So we could either have the ortho product or we can have the para product. Questions, comments? Yes. So the alkylation and isolation, we're going to go back to the Friedel-Crafts section and talk about it next time, just because I want to make sure we're all good with it, but it entirely depends on what the substituents are. So in this example, could you do a Friedel-Crafts reaction? Exactly. So in this one, you could do it no problem. But if he gives you something like this, now you have an NH2, so you could not do Friedel-Crafts. So it would just be no reaction. Similarly, let's go back to one we've already done. If this was a Friedel-Crafts reaction instead of a halogenation, Would that happen? No, because there's a strong deactivator. Cool. Sort of kind of makes sense-ish? Okay, so we're going to do one more example, and then we're going to spend the last couple minutes just recapping. So let's do this one. Mix it up a bit. Did someone have a hand up, or did I just imagine that? Okay, cool. So SO3H, what kind of group is that? It is definitely a deactivator. Is it a halogen? No, so it's going to be a strong deactivator. Cool. And if it's a strong deactivator, it's going to direct where? Meta. Cool. Alrighty, now the R group, activator, deactivator, what do we think? And where does it direct? Orthopara. Coolio. So between these guys, between a strong deactivator and an activator, which one is a stronger activator? The R group, yay! So yes, there will be questions like this. They're not all going to be super tricky and close with one another. Sometimes you'll just have an activator versus a deactivator. So the director in this case will be the R group, and it's going to do ortho, para. The second ortho position is taken. So again, we're only going to have two possible products. Oof, that was ugly. Oof, for real. Okay, so let's add our bromines in here. We could either have the para product or the ortho product. I think I heard someone say, wait, what? Was that a question? Look, okay, I didn't come here to be mocked there. There, a plus, are you happy? Anyway, fine, go to Katrina's session. She'll draw nice plus signs. Okay, so we have 2 more minutes. We're going to do a quick recap of everything we've done today. Any questions? Yes. 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 Mm-hmm. Yes. So if it was like this, yeah. So if it was like this, right? This guy is still the stronger activator. So it's going to go ortho. The pair position's already taken. So you would just get one product that's ortho. Okay. So I lied. We're not going to do a summary because we're out of time. But if you have any questions, I will be here. If not, have a wonderful day, and I will see you on Friday. Or not. Whatever. You're welcome. Okay, so you're on to something. The only thing is that that's